We now talk about torque on a rectangular current loop in a uniform magnetic field. So you consider a rectangular loop and there is current I flowing in it, and it is lying in a uniform magnetic field. Now this loop is parallel to the magnetic field, as you can see in the figure below. So first notice that this side 1 and side 3, they are parallel to the magnetic field. So you know that the force acting on the magnetic field, this is given as I L vector cross product with P vector. So first focus on side 1. You see that L vector is basically the direction of the current. So the current and B vector, they are opposite to each other. So sine theta would be 0 here. So this will be ILB sine theta. So for case 1, this theta is nothing but 180 degrees or pi radians. So sine theta would be 0. So force acting would be 0. For side 3 now, theta is 0 because this current and the magnetic field are in the same direction. So theta is 0. So again force would be 0. So we are now just going to worry about side 2 and side 4. Now for side 2, you can see the angle. So we are going from I to B. So if you're going from I vector to B vector, or correspondingly you can say the length vector to the magnetic field, more correctly, you have an angle of 90 degrees here. Similarly on the side 4, you again have an angle of 90 degrees here. So for sides 2 and 4, theta is pi by 2, or you can say sine theta is just 1. Now let us look at top view of this. Now if you have a view from the top, you will see that the force 2 is acting upwards and force 4 is acting downwards. So we are looking now from here, from the top of the rectangle. So we are looking down. This is the top view. And top view, this is side 2 here and side 4 here. So side 2 is here. The force acting on side 2 acts upward and force acting on side 4 acts downward. So this you can see by the right hand thumb rule by taking the cross product of L vector and B vector. And these two forces cancel each other out. But they introduce a torque. These two forces are equal to each other, so they should cancel each other out, but they produce a torque because they are acting at different points. They are not acting at the same point. So now they produce a torque. So the torque is given as the force times B by 2. So that is what we have, the torque right here. So torque is F2 times B by 2 plus F4 times B by 2, because B by 2 is the length right here. So F2 and F4, we determined it to be ILB. So F2 and F4 was ILB. Sine theta we took as 1 because theta was pi by 2, and L is the length. So this length we are taking as A. So you're talking about side 2 and side 4, we are going to consider this length as A. So instead of L, you plug in A. So you have F2 and F4 as IAB. This IAB you plug in right here and right here. So you get IAB and capital B for the magnitude of the magnetic field. Now consider case 2. The coil makes an angle theta with the field. So you take the magnetic coil, what we have right here, and this coil, you take its normal. So this is the normal of the coil, and this normal makes an angle theta with the field. So the field here is in green. So the magnetic forces on side 1 and 3. So this is side 1 and this is side 3. So there are forces acting on these sides, but these forces act along the axis of revolution. So say the axis of revolution is right here. So the force acting on 1 would be right here, and force acting on 3 would be right here. So these two forces cancel each other out and produce no torque. since they both act on the axis of revolution. For forces F2 and F4, we again use the formula, and now you have an angle of sine theta in here. So again, if you put theta equals to pi by 2, you get the formula right here. So here you have sine theta, and you can see these forces here also in this figure. You have F2 acting here and F4 acting here. So the torque is given as F2 times B by 2 plus F4 times B by 2. So same formula as before, but now F2 and F4 are different. F2 and F4 are IAB sine theta. So we plug in IAB sine theta here, and this is what you get as the torque. Now if you put the area as A times B, so this area is the area of the loop. So you can see the length is A and the breadth is B. So the area is A times B. So this is A and this is B. So instead of AB, we can write the area vector. So we can write torque as the cross product of area with the magnetic field.